Hello, ladies and gentlemen. Can I have your attention, please? My name's Sandy Tudup, and I'm head of the School of Geosciences here at the University of Edinburgh. And it's a great pleasure to welcome you to this talk, which is both part of our Changing World series, but it's also a Carnegie Centenary lecture, and I'll explain that in a moment. So it's my pleasure to introduce our speaker today. It's Professor David Battisti, who's in the Department of Atmospheric Sciences at the University of Washington. Now, David trained as a physicist at the University of Massachusetts in Amherst, but then moved to the University of Washington, where during his PhD studies, he started looking at ocean-atmosphere interactions. And as part of his PhD, he did some of the most fundamental and pioneering work on understanding the El Niño climate phenomenon. So that's the climate phenomenon which is the largest source of year-to-year variability on Earth. And that work has really stood the test of time. Now, David's gone on to work on the El Niño, but also on a diverse array of climate-related issues, from very deep time issues, so going back millions, hundreds of millions of years, so looking at the impact of the drifting continents and the growth and decay of mountain chains on climate, through to climate that occurs on seasonal or shorter timescales. He's been a very articulate and active researcher looking at the impact of anthropogenic activities on climate change around the Earth. And he's also been a good critical eye that's tried to assess the potential of using geoengineering, so man-induced solutions to modifying the future climate in the face of climate change. But David is also one of the great collaborators, one of the great interdisciplinary researchers that's always sought out collaborations that will allow him to contribute to addressing some of the really big issues of our time. And that, I think, is going to be exemplified by today's lecture, where he's going to talk about that interrelationship between climate change and global food security. Now, David has won all sorts of honors. He's one of the most highly published and cited researchers in his field. And he holds visiting positions at the University of Stanford and at the University of Bergen. But he's here today because he's also won the very prestigious Carnegie Centenary Professorship, which is a professorship that's offered by the Carnegie Trust for the University of Scotland to allow us to bring to Scotland some of the most talented researchers in the world to share their ideas and expertise and build collaborations and future opportunities. And with that, I'd like to welcome our colleagues from the Carnegie Trust, and in particular, Sir David Edward, the chairman of the Trust. Maybe, Sir David, if you'd be willing to say a few words about the Trust and this opportunity.
Well, thank you, Sandy. The Carnegie Trust for the Universities of Scotland was founded in 1901 by Andrew Carnegie, who, of course, came from Dunfermline. And one of the things that he regretted most was that he had not had a university education. And he founded the trust for two purposes. One of them was to make it possible for any Scottish boy or girl to come to one of the Scottish universities and come with the fees being paid. It is put about in certain political quarters that higher education in Scotland has always been free. That is not so. And the fees charged by the universities made access extremely difficult. And through Carnegie and his legacy and his trust, his benefaction, it was possible for the many men and women to come to university. Of course, they came at the age of about 16 in those days, and it enlarged access to the Scottish universities enormously. That was one half. The other half was to go to the universities because the Scottish universities, by that time, in spite of their great reputation, had not kept up with the English universities and the German universities in science. And so half the annual income of the trust was to go to the universities to enable them to build laboratories, libraries, student residences, and so on. Well, today the trust, over 100 years old, is not able to do anything on that scale because of the fall in the value of the trust income, but we still have somewhere between 2.25 and 2.5 million a year to distribute. A large part of it goes to postgraduate scholarships, 15 scholarships a year to the really outstanding scholars who are just about to take PhDs, and another quarter goes to bursaries for students who want to do taught master's degrees. Otherwise, the income of the trust goes to various research activities in the universities, but as a project for the centenary of the trust, we decided that we should offer 2 professorships per year, which would make it possible for really outstanding scholars to come to one of the Scottish universities and take a full part in the work of the university, and also to give one or more public lectures in their chosen field of study. And so that's why we're here tonight, as well as the university's already series of lectures. And I'm delighted that Professor Battisti was able to come to Scotland, and also that he's giving this lecture tonight. Thank you.
Thank you very much, Sir David. And so with that, I'd like to pass over to our other David, David Battisti.
Thank you all for coming. I really am grateful to the Trust for allowing this to happen, and for trusting in me to uphold the values and the traditions and the goals of the Trust. And I'm very excited about being in Scotland to build these partnerships. I'm really happy also and very grateful to the University of Edinburgh for hosting me and making this all incredibly simple. So, and I could say a lot more, but I want to make sure I talk to you about food. And part of, actually before I should say this, to do interdisciplinary stuff, a lot of it depends on the culture that you're in. And the impression I have here from my short stay so far at the University of Edinburgh is that culture exists here. It's an extremely fun place to be, and there's a lot of different stuff going on. That's also true of my home institution, where it's just very easy to collaborate and cross boundaries and teach with various people. So I teach in the law school, and I teach with anthropology professors. And it's very exciting. It keeps you growing. And it keeps you finding problems that you wouldn't otherwise know existed, because you're in your little world, your little disciplinary world. So this is one of those that came about because of that, because of just a chance interaction with some agricultural economists, and led eventually to this. So I hope everyone had a chance to see the fun facts about food up there. So I'm just going to talk about the physical side of growing food. There's also a whole problem with social markets, economics, everything else. Just the physical part. The projections of food demand over the next 40 years or 35 years is it will need to double the production of what we're producing now. And that's really heroic. Basically, the rate of change or the rate of increase per year is going to have to be equivalent to what happened in the Green Revolution, which was a 20-year period between 1960 and 1980, where yields almost doubled, not quite. And basically, we have to do that. We have to do that for twice again as long. And it's going to be much harder because of the way things worked in the Green Revolution, the way they work now. So constraints. Land is a big constraint. if you look between 1800 and 1960, almost all of the increase in food production was because there was new land in use, like that was put in use, good land. There's really no more prime land out there anymore, and we're actually losing land at about, the prime land is being lost about 1% per year, just due to soil erosion, wind erosion, salinization due to irrigation practices. If you look at water, of course, water is already limiting in many places of the world. And climate change is not going to make that better because just warmer means more evaporation. Energy, green revolution was fueled by three things: increased, better yields, better plants, genetic improvements, irrigation, which was made possible by cheap energy, and forget a third one. Water power. There's a third one. Oh, fertilizer, cheap fertilizer. Right? So energy is obviously oil is becoming more expensive. That ran the machinery, and that also ran the pumps to pump water for the irrigation. Right? Nutrients, nitrogen's becoming more expensive, and phosphorus is basically a limited nutrient. And the lifetime of that is anywhere between 50 and 300 years is the estimate of how much phosphorus we have left in the world. And then there's climate change. And all these things conspire to make it really challenging to double the food production in the world in the next 35 or 40 years. So I'm just one slide that talks about where the food insecure live today. And then I'll talk a little bit about climate change itself, and then talk about just the parts of climate change we're absolutely sure about. There's kind of no way around. And what it implies for agriculture. There's some things you'd like to know more about, like changes in the intensity of precipitation, or where is it going to rain more or less. Turns out that's hard from a climate perspective. But there are things that are easier that actually matter. Okay, so where do food insecure live? Don't worry about the colors in this plot. There's about 1 billion, or 1/7 of the world population today, that's food insecure, meaning they don't get enough calories to live a healthy and productive life. They live in basically these colored countries, and you'll see all those countries are between, say, 35 degrees north and 35 degrees south, which we call in climate lingo the subtropics and the tropics. Right? Most of them actually don't own farms. Most of them are farmers, but they actually work for other people, and they're working to provide, to raise income to buy the food. And about 50% of their calories comes from 3 grains. Right? Wheat, rice, and maize. Okay. Stop me if you have any questions. I might ask you some questions. Okay? So I'm just going to talk about here the changes in climate that are very likely. That is, they're deemed to be greater than 90% chance to occur based on a quantitative analysis of all the climate models and the data out there, and or elicitation from expert views. Okay? And I'm just going to avoid things that we're not quite sure about, even though they might be important things, because we can't say much about them at this point. So how much climate will change depends on 2 things. One is how much carbon dioxide you put in the atmosphere, and the other is what's the response of the climate when you do that. So how much carbon dioxide is going to go in the atmosphere isn't really a science problem. It's a policy problem, it's a human problem, it's a political problem. It depends on population and economic projections, future choices of energy, governance, policy options, development, how much development there's going to be. All these things are really quite complicated. These scenarios are constructed by demographers and economists and politicians and everything else, and they're given to the climate science community to actually say, okay, if this happens, what will be the response of climate? So we don't have to go through this really volumes of literature on how you do this. You can do this one calculation. You want to say how much carbon dioxide is going to be in the atmosphere at the end of this century. And I'm going to, you guys have to do this. So let's assume the global population increases from 7 billion today to 9.5 billion in 2050, and then basically levels off at that, okay? Which is what the projections are right now. Poor people develop. That's a good thing, right? But anytime you take people from the underdeveloped world and you develop them, they use more energy, right? They want to live at a higher standard of living. So let's say that poor people actually develop. That's a good thing. Population increases by about 1/3, And the current emissions of carbon dioxide today don't change. So we do all that. We add a third more people, they all develop, they use more energy, and emissions of carbon dioxide don't change. What do you think the odds of that are? That emissions don't change? They're going up at a really rapid rate right now per year. Okay? So that's a pretty conservative estimate, right? So I'm going to tell you that the concentration of carbon dioxide in the atmosphere today, measured in these units we call part per million, is 400. Before humans started doing big time stuff, it was 280. That was 150 years ago. Now it's 400, and we're going up 2 per year. So if we go up 2 per year for the next 85 years, how much of an increase is that? 2 times 85. Who's got it? Come on, come on. 170, right? 400 plus 170 is? 570. Don't be shy. Okay, 570. Okay, we started out at the pre-industrial, before the Industrial Revolution started, and we started burning a lot of coal and oil. We started at about 280, so this is a doubling. So we're going to double carbon dioxide by the end of the century, even under very conservative estimates, right? Okay, now you can get a bunch of people in a room and they'll come up with all sorts of things like how population is going to grow, how they're going to develop, what the energy choices are going to be, and they'll give you all sorts of scenarios for how much carbon dioxide is going to be in the atmosphere. So here we are today at 400 in 2010 or 2015, and here are these different scenarios, and the scenarios differ by assumptions about how population is going to change and everything else. A2 is called business as usual. It's a world like today where people are moving more towards renewables because they're cheaper, but they're doing it on a kind of country by country, or in case of EU by US, unevenly, right? It's assuming the population peaks in 2050 and declines, right? It's called the business as usual scenario, and that peaks at about 850 instead of today we're at 400, right? If you look at this scenario, B1, this is, everyone calls this business as usual. I call this one utopia. This is a world where environmental problems are the very first concern. Global governance, right? There's an agreement that environment's important, population peaks in 2050 and declines. You immediately curtail fossil fuels and you move to renewables. Sound like a world you know? Right? So I call this utopia. It's not going to happen. A1B is split the difference. And everything I'm going to show you today is splitting the difference. It's like I have some optimism here, right? More than just business as usual, but I'm not a dreamer. Well, at least not for this purpose. Okay, so let's look at this now. Oh yeah, by the way, if you want to stabilize the carbon dioxide so it doesn't keep on going up in the atmosphere, you have to get down to 100 kilograms of carbon per person per year. Okay, now Scotland actually produces like 2,100 on average, right? So you're 21 times what you're allowed if you want to level off CO2, not have it increase anymore. In the US, we're actually 55 times higher than we need to be. But actually, Scotland is coming down amazingly fast. You are going to meet the 100 kilogram target. But you're the only country in the world it is. And I was really impressed. I plotted up last night and thought, wow, I was going to show this slide, but it's actually not impressive. But it is impressive because you guys are going to meet this target way before 2100. But no one else in the world is, right? So actually, not much has changed. So the new IPCC report just came out last year, and the summary report just came out on Sunday. And really not much has changed. I would just say that the terminology has changed. The business as usual scenario used to be called A2, now it's called RCP 8.5. It's CO2 peaks at about the equivalent of CO2 if you include all the other greenhouse gases at 930. And the global average temperature increases on average across all of the different models of 3.4 degrees by the end of this century. Utopia is now called RCP 4.5. And it's 530. And there's a global average increase of temperature of 1.8. And split the difference between these things is now called RCP 6.0. It's 670, okay, and it's a 2.8 degrees C increase over what we started with at the beginning of this century, so 15 years ago. Okay, now it turns out that if you're interested in temperature, whatever you get with this scenario, this split the difference, if you think utopia is the world, everything I show you just multiply by 0.7 today and you're good. And if you're pessimistic and think it's going to be business as usual, everything I show you today just multiply by 1.2, and the answer is about the same. I don't have to show you endless slides. It works out really well. Swap this vocabulary, and the results and the conclusions from the 2007 report are the same as 2013. The latest report adds one more emission scenario, the 2.6, which is like, ridiculous. And basically, it means that you stabilize CO2 in the next 30 years and you bring it down. Right? You actually take it out of the atmosphere, which is very expensive to do. It's put in actually just to show you that it's almost impossible not to exceed at least 2 degrees C by the end of this century, which, if you believe Nicholas Stern and other kind of mainstream economists, that's too dangerous. 2 degrees C is too dangerous to reach. Okay. Okay, so where are we at? Here's the CO2 in the atmosphere, carbon dioxide, from 400,000 years ago, bopping up and down, to about 10,000 years ago. 10,000 years ago, it's here. 150 years ago, it was here. Today, it's actually here, right? And these things, when you go up and down here, this is the difference between an ice age and a not ice age, right? So when you're down in this bottom point here, there's actually about 1.5 kilometers of ice sitting over you guys. 3 kilometers of ice sitting over us, right? And then when you're out, it's actually kind of more like today's climate. And here we are, we're up at 400. The difference between 280 and 400 has just been what we've put in so far since the Industrial Revolution. And that's where we're going to at a minimum by the end of this century, okay? So, and this is all due to basically burning of fossil fuels. A little bit due to agriculture, but increasingly it's more and more so the burning of fossil fuels. It's more than any time in the last 3 million years. The rate of change is about 100 to 1,000 times faster than nature can do it. And it takes nature to restore this. If you just said, okay, I'm going to stop emitting everything now, and we're up at 400, how long is it going to get back to 280? The answer is many thousands of years for nature to do this on its own because of the way the chemistry of carbon works in the ocean. This has been known for over like 60 years. By the way, what happens when you double carbon dioxide in the atmosphere? What happens to the global average temperature has been known for since 1896, so almost 130 years. Okay. Okay. So what's happening here? This is a temperature. The black line is the observed temperature, global average. This is relative to like the end of the last century. So 0 just means it's normal for the end of last century. If you go back to 1900. It was about 0.85 degrees colder than it was at the end of the 1900s, so like at the year 2000. Here's the projections. Let's just look at one line, the green line here. That's the split the difference between business as usual and utopia. And the green line is averaged over all the climate models, right? And the light green here is just the spread of, like, some climate models don't give you as big a change as other models do. But on average, the temperature increase from 2000 to 2100 is 2.8 degrees. What was the increase over the last 100 years? I just said that number. 0.85. So 0.85, 2.8. So it's 3.5 times more increase over this coming 100 years as was over the last 100 years. Okay. Now, and there's uncertainty. Given the same amount exactly of scenario of where CO2 is going to go, climate models give you a different answer. Some of them are kind of wimpy and say, well, maybe 1.4, but some of them say, 2.4 here in the green, and some of them say 3.2, right? So there's some uncertainty in the climate models of what's going to happen. Now, here's this blue one is utopia. And it says, okay, if I put less CO2 in, all models tell me it's going to be less warm, right? But it still warms. No model tells you basically it's going to be less than 1.2 degree warmer than it is today. In fact, the odds of it being even under the kind of the lowest emission scenario with the wimpiest climate model, the odds of being only 1.5 degree warmer at the end of this century are basically 0. Okay. I think I'll just stop there on that slide. Any questions on this so far? The food stuff is cool, but this is really important. Okay, so here we go. This is 1900. Now this is a blow up. This goes from 1000 AD. There were people here, but there weren't people, well, there were people in the US, but Okay, sorry. 1900, 2000, this is this 0.85 degree increase. Here's the spread going to the future for the next 100 years. And it depends on the emission scenario. Each one of these colors is a different emission scenario. And the range in the bar, for example, this red here, is the differences between the models given the same emission scenario. So what you see from this plot is there's uncertainty in what's going to happen in the future. It's kind of equally due to we don't know how much CO2 is going to go in the air, which depends on people's decisions. And we don't actually know, given the exact profile of CO2, we don't actually know exactly what the climate's going to be. There's some uncertainty there. And I would say roughly the uncertainty in the projections for the next 100 years are roughly equally split between those two things. Okay? For reference, here's the temperature or an estimate of the temperature from proxy data. It means they're not direct, no one's measuring temperature back here because there's no thermometers, right? But there's indications from trees and corals what the temperature was. And basically, you can see you have to go back at least 500 years before you get to a temperature that's as warm as today, and probably you have to go back at least 1,000 years. Okay? The data are just not good enough to quantify that. Okay, now, for this split the difference emission scenario, the global average temperature increases 2.8 degrees. This is the change in temperature, the end of this century minus the end of last century. Global average is 2.8. Does everyone get the same? No, right? Look at this little spot. If you live here in the North Atlantic, right, then the temperature change is only maybe 0.5 degree Celsius. It's understood. We know why that's the case there. It's a very special place in the world. But if you look at land, okay, you tell me, land and ocean, the same? Which more? Land, right? This was predicted 120 years ago, actually. If you look over land, the average here is somewhere between 3 and 4 degrees, right? So instead of 2.8 as being the global average, if you live on land, you're looking at more like probably 4 for the split the difference emission scenario. Okay? So oceans, not as much as land. And in the annual average, the Arctic warms a lot. Why is that? Albedo. That's the normal answer. I mean, that's the party line. It's mainly that sea ice melts. And when sea ice melts, then in the wintertime, the ocean, because actually the biggest warming is in the winter when there is no sun up there. So basically, the atmosphere sees water instead of land, right? And so most of it is you're actually creating more ocean. But then there's an albedo feedback, which is not trivial. It's just not the dominant player here. Okay, good. So there we go. So if you're an optimist, multiply everything on this map by 0.7. If you're a pessimist, 1.2. Okay, so about 3 to 4 degrees C increase over this century due to this split the difference emission scenario. Now, when it comes to rainfall, there's not a lot we can say. We can say basically anywhere it's stippled here, it means, I'm never going to describe this right. Models give you a whole range of answers. The difference between the models is smaller than the distance between today and the average of all the models. Does that make sense? So if this is today, and the models are all over the place up here, the difference between the models up here is smaller than the difference between here and here. So it's where the models say, yeah, it's going to change, but we actually don't know how big it's going to be. There's a lot of uncertainty. So basically, red here means it's going to be less rain. So Central America, Southern Europe, less rain. Subtropical regions here in general, less rain. South Africa, a little bit of Australia. Blue dots here means more rain. And that's simply because there's more moisture in the air when you increase the temperature. Therefore, the same storm that brings moisture in is now bringing more moisture in, and it just rains more. It's not rocket science. Okay. So there's robust drying in the subtropics. Okay. Now, let's see what this means. So that's about all we can say. Well, no, we can say a little more than that. But for food production, those are the things we can say with confidence. Over and over again for the last 30 years, climate models have told us those things. Okay? Answer doesn't change. So let's first look at precipitation. Here's the projected changes in precipitation. In Europe, right here. Does everyone see this here? I should go over here to be a little equitable. Europe, okay? This is wintertime, this is summertime. Dark brown here is a 50% reduction in rainfall. Right, these are really big. reductions in rainfall. In the annual average, you're looking at a 20 to 40% reduction all through Southern Europe, all through the stands here, Tajikistan, Iran, Iraq, all these places here, 20 to 30% reduction. In the US, this is where I would tell you, the Dust Bowl is a famous thing in the US where clouds of dust came from the central of the US, which would be kind of like the equivalent of Prague, and blew into Washington, D.C., which would be like Edinburgh. And when people were debating like what to do about this problem, and these things, and all that way, this dust came in and just turned the sky black in Washington, D.C. That was a reduction of precipitation of 7%, right, for a 10-year period, which is a lot for a 10-year period. But this is a 20 to 30 to 40% reduction forever, right? So luckily, well, not so lucky for the people who live there, but there was a drought that was this big for a 3-year period in this region here. So here we go. This is 30% reduction in the annual average rainfall all through Iran, Iraq, Afghanistan, Pakistan at the last century. And you can say, well, what happened in these places, right? And the answer is in Iran, 80% of the livestock was lost. Right? Afghanistan, 40% of livestock. There's typically 50% reduction in grain yield, right? Big loss in livestock. Anyone know the way you do livestock in these parts of the world? Like in upstate New York, where I grew up, we would put the cows in the barn and we'd roll out some nice hay and silage, right, for them. These are grazing animals, right? So basically, the livestock are lost because the grazing lands are in trouble when you have this much rainfall reduced. So this is going to be normal at the end of this century in this region. That's one thing that's reliable from the climate models. And it's not something you really adjust to other than give up livestock, right? Which, if you know the cultures of these regions, is a big deal, right, to do that. Okay, so that's precipitation. Not much we can say there, but it turns out that temperature is a much bigger story for the future in agriculture. And this was a big surprise to me, and it might be a surprise to you too, growing up in Scotland here, where it's kind of cool and wet. Okay. This is a picture of the summertime change. The stippled means the models are the difference between all the models is small compared to what the models say about the future compared to today. This is a 4° C change, basically, at the end of this century in almost all land areas, right? Unless you get right down here, which is kind of actually ocean anyway. The continent's so small that you don't see much heating there. Okay. So about a 4° C change. Now, nature did this experiment for us too. France, 2003, 3.6 degrees Celsius, average summer temperature compared to the normal for the last 107 years, right, of data that we have. And when that happened, you had a lot of people die, heat stress. You had about a third drop in maize yields, 30% decrease in maize and fodder production. Fodder production just producing food for animals instead of people. 25% decline in fruit harvest, 21% dry yields. If this was due to drought, this would happen every 3 years, right? There was nothing really unusual about rainfall in France that year. It was heat. This is heat. By 2100s, years of similar temperature stress on agriculture will be the norm throughout the tropics and subtropics due to summer average temperature change. It turns out that for most of the crops, summer average temperature is a really good indicator of how much yield you get. This was a surprise to me growing up upstate New York, and I'll show you why in a second. It'll be pretty obvious. Okay, how am I doing on time, by the way?
Another 20 minutes.
Okay. Okay, so the first meeting I went to was at the Svalbard, the seed bank, at the very first slide. Right? I was there to talk to people about what kind of seeds they should be looking for if they're going to prepare for 2100. And everybody the first day was really excited. All these breeders were there and seed collectors from all these seed banks around the world. They're all talking about temperature. And I came prepared to talk about what little I could say about rainfall, because growing up in upstate New York, that's what we cared about. Did we get enough rain at the right times for growing corn for the cows, right? So it really surprised me. And the person sitting next to me, who turned out to be my agricultural economist friend now, who I write papers with, said, gee, do you think it would give them an idea of like how much temperature is going to change in the future? You know, they're really interested in temperature. I said, yeah, that's easy. So I wiped off all my slides. I went back to the room. I had all the data on my laptop. Did these calculations. This is the calculation I did. So here's the observed temperature in France, summer average temperature. Over this last 107-year period when I actually did this calculation, we had that data. 0 means normal for that 107-year period. So a really cold summer, the coldest on record, was about 1.7 degrees colder than the average, if you average overall summer. And then the warm one up to 2003 was maybe 2.5 degrees above normal. And then here's 2003, way out there, right? So it was a big surprise. So what I did is I went to all the climate models. I said, what do they say about the average temperature change? I assumed that the natural variability was going to be the same. You still had this spread here, like this. And I said, let's interrogate all the models and say, what's that distribution look like at the end of 2100? So this would include the model with the wimpiest mean change and also the biggest mean change. Okay? And the answer is this. Okay. So this is using this intermediate emission scenario. And that's what it looks like at the end of this time period. So this tells you what it looks like in 2090. Right? What's the average? What's the most likely? Yeah, 3 or 4. It's France, 2003. Right? That's the most likely. There's a tiny, tiny, tiny chance it's going to look normal. And there's a tiny, tiny chance it's going to be 10 degrees C warmer summer average temperature, which would put you in the middle of the Sahara. Right? That's hot. Okay? Now, if you do this for the Sahel, Africa, the tropics are famous for being steady in temperature. So here's the 20th century record. A really cold summer is about 1/4 degree colder than normal. And a really warm summer growing season is 1/4 degree warmer than normal, right? And here's the projections for 2090. So how do I read this? What are the odds that the temperature is going to be normal? 0. What are the odds it's going to be greater than anything ever recorded? 100%, right? The odds are basically 100% that by the end of the century, the temperature in the Sahel and Central Africa are going to be greater than anything ever seen. Right? Now, I can show you histograms for all the places in the world like this, but instead I'm just going to show you a map that shows what are the odds that the summer in 2090 is going to be greater than the highest temperature ever seen at your place in space. Red means basically 90 or 100%. And you can see basically most places in the world, if you go from like the US, all through Southern Europe, Asia here, all the way down to Northern Australia, all of Africa, right, and tropical South America, are out of bounds. That is, the temperature that's going to be seen, 100% guarantee that the temperature, summer average temperature at the end of the century is going to exceed the highest temperature ever seen, right? Now, this turns out to be really important for food security, and this was news to me. And actually, I should say, when I showed those histograms to the people in the room, I didn't have this map yet, but I showed a bunch of histograms for like Nigeria and Iowa, where we produce a lot of corn in the United States. I showed these plots, and there was like nothing. Everyone just sat there. It's like, and I thought, oh man, I misunderstood something, or maybe it's not important, or maybe I just didn't communicate it right. And the guy who's chairing the meeting stood up and he goes, we got to really completely rethink what we're doing. And I thought, wow, excellent. I mean, just because you feel like, okay, there's something there. There's something that they really needed. I had no idea they needed, right? And it's just these kind of meetings, these chance meetings that you get together, people from disciplines, and you find out that there's real opportunities. In this case, unfortunately, the news is really bad. But you can, from this, you know how to move forward. You know what you need to do. So most of the tropics and subtropics, the seasonal average temperature will very likely exceed the warmest on record. That is greater than 90% chance. Right? Now, what this means for crops, this is every dot here is the yield for a year, for a season. And this is in northwest Mexico, where it's the green revolution for wheat. It's where wheat yields went from 1.5 tons per hectare to 5.5 tons per hectare, because of increasing yield and irrigation and everything else. These are perfectly irrigated plots. They have way too much fertilizer, way too much nutrients, way too much pesticide, right? And yet, if you look at this, basically yield is a really strong function of temperature. As temperature goes up 1 degree, yield goes down 10%. Everything else is perfect for these plants. This is just temperature, right? This is just temperature. Okay? Oh, wrong thing. Go. So why? It's interesting. It turns out this is a very basic physiological response to plants. That once you're beyond what's called the optimal temperature for a plant, what happens is the spikelets on the top of the plant where all the grain comes out become less fertile. So you're actually just growing less grain out. The other thing happens is the plants actually stop growing sooner. They grow faster, but they stop growing sooner. And all the grain actually comes out and fills the head, the husk, at the very end of the plant. So if the plant stops growing, it doesn't fill, right? So there's a very strong relationship between the mass of grain and the temperature, and it's a negative one. If temperature increases, the mass of grain goes down. There's increased water stress, right? Which wasn't the case here because they're irrigating, right? But hotter conditions mean more stress on a plant. And there's increased respiration. It turns out under higher temperature, respiration increases faster than photosynthesis does. So there's a lot of reasons why this happens. And it turns out it happens not just in wheat in northwest Mexico. The breeder for wheat in India said the same thing. I have these plots in India, and I measure a 15% decline for every degree C increase I've seen, right, in northern India. 17% decrease for every degree increase in the Philippines in rice production, right? This is not just a wheat phenomenon. It's not just a rice phenomenon. It's soy. It's all the major grains, right? It's especially important for these crops, right? Which are basically the what do you call it? The foundation for calories in the world, right? Okay, so 10% per degree C warming under optimal otherwise conditions. Plenty of water, nutrients, fertilizer, pesticides. What does that mean for production at the end of the century? 10% per degree C, how many degrees? 3 to 4. So optimistic scenario would be a 30 to 40% decrease in grain production. Due to this, those are under idealized conditions. Add water stress, add nutrient stresses, and it just makes it worse, right? So this is, this is life for Middle East, India, Southern Africa, right? Increased volatility of crop yields. This is probably the one last science thing I want to get across, and then I can wrap it up pretty fast, I think. Well, I could go on forever, but this one, I didn't realize this. Even though we'd done all that work on mean temperatures, and we were talking about the tropics are way past this optimal temperature for growing things, I didn't realize it was actually going to mean a lot for the US and for Europe and Ukraine and China, the breadbasket countries of the world where most of the food is produced. This is actually huge, not because the mean changes, but because the natural variability in the mid-latitudes is pretty big. So even if you have a small shift in the mean, this natural variability will mean that some years will be really devastated because it'll be way beyond the optimal curve. So let me show you this in a cartoon. Hopefully this is going to work. So this would be some indication of yield, where one would be like the best you can do under optimal water, everything else, sun, it's the perfect year. It turns out that everything has an optimal temperature. Mine is probably somewhere around 15 Celsius, I'd say. Anything beyond like 25, and I'm really not good. Okay, so I'm kind of like a plant. This would be a plant curve, right? 25, 26 average summer temperature is a really good temperature for a lot of grains. 24 might be even better. And basically, as you go to higher temperature, it drops off really fast. So when it gets much hotter, basically yield goes down really fast. And of course, when it's colder than the optimal, it's also not good for a plant, right? And all these curves for plants, for organisms, for humans, actually look like this, okay? Just that where the peak is different, okay? So let's take a look here, and that's today. If you live in a place like central US, Russia, Europe, China, that's the average summer temperature. It's around 27 or so. And the year-to-year variability might be plus or minus 2 degrees for a really cold and a really warm event. So you're wobbling back and forth. Now, if I look at what that means for yield, it means I'm going between here, and I'm really close to the optimal. Right? So growing up in upstate New York, we didn't care about temperature because we are on the optimal. And even in a cold year, we're close to the optimal. And in a really hot year in upstate New York, we're close to the optimal. Right? So, you know, the swings in yield are only just maybe 10% due to temperature. And that's why in Europe and in Ukraine today and in the US today, you're mostly worried about rain. You're going to get enough rain at the right time, which is hard for us to deliver from like what's going to happen to changes in rain. But if you just shift this a couple of degrees, like we're expecting at the end of this century, and I say I have the same climate variability, I'm just 2 degrees warmer on average, and I look at this, now I'm going everywhere between being, well, like today, to being, 0. Everyone see this? I mean, I must admit, I completely missed this. And actually, surprisingly, this is still not well understood in the public, or even in agriculture circles. Okay, so if you now look into the future, you see even just with a 2-degree increase, because of this really steep curve here, you're going all over the place from one year to the next. So in the mean, yeah, you're down a little bit, but the important thing here is that the volatility is huge, right? And it's not the climate that's more volatile, it's the crop response to this changes in temperature from year to year. So here's a plot of this. This is the average yield today, say 0. These are the departures from the average yield. The blue line would be what we see today. How much departure from normal do we see just due to natural variability today in yield? Well, there's a slight chance here you might get 8% more if you just happen to be perfectly on the optimal, because today we're actually a little bit, this is for Iowa, but this works for any kind of mid-latitude location. There's a slight chance it'd be a little higher. There's a slight chance it'd be a little lower, right? But there's not much sensitivity. But if you actually just go 2 degrees warmer, 2 degrees global warming here, the green line, the average yield goes down. But the more important thing is you pretty much can get yields all over the place, right? So if you're a farmer now, this year might look pretty good, normal, but next year might look like nothing, right? And you can ask the question, well, how often do you see a 10% decrease in yield today due to this temperature variability? And the answer is you have to wait like every 32 years, which is why we didn't worry about temperature upstate New York. And that's like France's thing. It's like you have to wait a long time before you see temperature actually do some damage. But if you look at the future, just with a 2 degree C increase, so now we're talking 2050, we're not talking 2100, we're talking 35 years from now, basically you're guaranteed to be 10% loss every year. But the more important thing is you're losing 25% every 4 years. Right? Now, you can't run agriculture in the broadcast countries if you're losing, at least not in the United States, because you need a lot of crop insurance, and we already spend $80 billion a year in crop insurance. Taxpayers do in the US, right? You can't keep that up. So you have to do agriculture fundamentally in a different way. In the US for sure, in Ukraine, Europe, right? The only possibility is that you engineer your plants so they stay on the optimal. As the climate warms, you stay on the optimal. Turns out that the International Research Institute's been working on this for 30 years. They've known about this heat effect for 30 years, and they've made no progress on that problem. Yeah?
Sorry, I thought you said no problem, but no progress.
No progress, yeah. And they all differ for like what's most important. Is it respiration changes? Is it the plant stops growing sooner? Is it heat stress? Is it water stress? They all differ. I mean, they will measure corn in Iowa, they'll measure it in California, and they'll come up, they know the answer for there, but it's a different answer. Now that's actually even worse, because it means there's no silver bullet like there was in the Green Revolution, where you can just make varieties grow shorter so they can put heavier grain on top of it, they don't fall over. Right? There's nothing like that in this problem. Heat's a really complicated genetic trait, and it seems to be what's causing the reduction in yield is different in India than it is in Philippines or Mexico. Right? Okay, so you have increased volatility of crop production. You have reduced nutritional content. This is not my specialty, but when you grow grains under higher temperature, it has less protein in it. Not that you get most of your protein from grain, but that's the case. Actually, but plants are also, for some reason, maybe it's just because they're stressed, with lower protein levels, they're more susceptible to diseases. How am I doing on time? Oh yeah, good. Increased disease transmission rates. Well, viruses like temperature, right? So when temperature goes up, and so do ectotherms. It turns out pests. Oh, I'm going to show you something about that in a second. So basically, disease transmission rates in plants go up, and in the soil as well as temperature goes up. You have loss of water stored in snowpack and glaciers, like for example in the Himalaya and the Sierra, and where I live in the Cascades. Not much you can say about precipitation. You do know in the subtropics, the Caribbean, Africa, Southern Africa, Northern Africa, Middle East, these are places that are going to dry. Strangely enough, you have increased frequency of duration, intensity of droughts. But where are those places are going to have, say, more frequent droughts and more frequent rainfall? These are harder things to actually get a handle on right now. We're working, well, we want to say we, the community is working on this. It's a very difficult problem. But the impacts of changing precipitation in these areas where we understand why precipitation is going to decrease in the air, it's very basic stuff. It means basically you reduce yields. In addition to the yield loss due to increasing temperature, you're going to reduce yields because precipitation is going to go down. And in a lot of places where you're growing staple crops now, those will have to be abandoned and substituted for other crops. Duration, intensity of monsoons. One thing I don't really fully understand, it turns out that almost all the monsoons on Earth get shorter. They're more intense. You get more rainfall because there's more vapor in the air, but monsoons get shorter. This is not something I would have looked at, but actually it matters a lot in Indonesia. And how this goes is Indonesia has a monsoon season just long, rice. It's the main staple, right? And you can't grow rice until you have enough water. So you wait basically until the monsoon starts and you've accumulated enough water and you put I can't remember the name of it, but you grow these like bunches, dense plants, and then you put them in the fields, right? They have enough water. The water lasts long enough to grow 2 crops of rice in a good year. El Nino years, it turns out, delay the onset of the monsoon. And so you can't always fit in 2 crops of rice. So production of rice in Indonesia actually is almost perfectly correlated with the start date of the monsoon, which is perfectly correlated with El Nino. And so I wouldn't have been looking at this problem if we actually hadn't been, we provide rice forecasts for the government of Indonesia, helping them to stabilize prices for free, I should say. It takes me 5 minutes every August to do this. It's a really simple thing to do, and it's very reliable. Out of 14 forecasts, we had 1 bust, and it wasn't a bust on our forecast, it was a bust on the users. We gave it to an organization that we said buy no rice this year. Usually we tell them like buy 1, 2, 3 million metric tons of rice. Just put to, in August, cheap because it's 9 months in advance when they need it. They put them in place basically, and people don't have to, basically if you're a farmer and you know you can't grow enough rice, you lay off all your laborers. So laborers go to the cities and they're just living on the streets. So the government in Indonesia just tells us these forecasts keep about 15 million people a year above the poverty line that would otherwise be under it. So we had these trusts already, we were giving them it, but we gave it this year and said, don't have to buy anything, it's gonna be a great year. And it was an election year and the president wanted cheap rice in place, so they bought a lot of it. Anyways, it wasn't our fault. I actually don't even remember how the election came out, but okay, so it turns out that all monsoons get shorter under global warming scenario that we've looked at. And actually, certainly I don't understand this, and I don't think our community understands it, but it's obviously very important in some places. So it's something to look at that came about because of this synergy between climate scientists working with economists and agricultural planners. Increased flooding in mid-latitudes and tropics. The intensity of rainfall just goes up, and that's simply because there's more vapor around. So the same storm is going to collect more water, and it's just going to rain more. Right? That's a really basic thing, and all climate models tell you that. When it rains, it will rain harder. But they don't tell you if where it's going to rain, it's going to change. Well, they do, but you don't believe it because the models do it really differently. Leaching of nutrients in soil. Heavy rain on soil leaches nutrients, which is not good because that's the food for the plants. Increased carbon dioxide. Carbon dioxide is a food for, if you're a C3 pathway through photosynthesis, carbon dioxide is a food. And if you take a plant, a C3 plant, such as soy or wheat, and you put it in a greenhouse and you sterilize the heck out of this greenhouse. So you're just left with a plant with a lot of water, a lot of fertilizer. And you double CO2 and you don't change the climate, you get about a 10 to 15% increase in the yield. That's good. But if you do this, actually, the same experiment in the wild, you just flood a plot with CO2 and you have the same climate, it turns out you don't get any increase. That's mostly because the weeds do better. Okay, basically, that's the way I understand it. Right? So really, this is like a non-factor. The temperature increases due to the increase in CO2 outweigh any benefit of just more CO2 in the air, and basically yields go down. Hot temperatures, dry soils break down the organic material in the soils. That's the food for the plants. I already said this, the disease. Sea level rise, that's not a good thing. It pushes salt water into the groundwater, which is not good for plants. And changes in pests and pathogens. I'm not going to go through this whole model. I'm just going to say we've a chance encounter with me, a biological evolutionary ecologist and a geochemist made us realize we could actually get a good estimate of what was going to happen to the pest population on the planet for crops. The answer is it basically doubles at the end of the century. And doubling, what does that mean? Well, you know, it means that for the big producing countries in the world, you lose about $10 billion a year. This is like small potatoes, you know, when you think about it. But the more important thing is, if you double pest population, you have to double pesticide use, right? Or you have to do something to account for that. So it's already a problem today, and it's just increasingly a problem in the future. Okay? So summary, by 2100, the growing season temperatures will very likely exceed the highest on record throughout the tropics and subtropics. Under really optimal, otherwise optimal conditions, which obviously you don't have, you're looking at 20 to 40% reduction in yields of all the major crops just due to basic plant physiology. Increased volatility of crops in the mid-latitudes, the breadbasket countries, US, Europe, Ukraine, China, Australia. In the subtropics, crops will be further stressed by reduced rainfall. Increased CO2 fertilization effect is small, less than 10% for a CO2 doubling. And pests and pathogen loss is about double. Yeah, and that's probably a downer, huh? What can I say? None of this is necessary, right? You don't have to get to a doubling or a tripling of CO2 if people don't want to. It's a very different world. As I said, you know, if you produce 100 to 200 maybe kilograms a year, if you want to get down to a point where CO2 doesn't increase in the atmosphere per person, which means I have to run on 2% of my normal CO2 budget in the US. It means the flight I'm going to take tomorrow to Stockholm basically is 4 years worth of emissions. One flight, right? Well, 2 flights actually, because I have to go to Amsterdam first, right? But there has to be, there are other options. They're expensive and they're expensive for people. Some people have a lot of resources. There are opportunities for other people, right? And it's more of a political and social discussion. It's not a science thing. Okay, thank you.
Hello, thank you very much for that. That was a fascinating talk. My name is Kate Smith, and I've just finished my PhD on the global governance of food security at St Andrews University. Part of the problem is the status quo, and the status quo is no longer an option. And I know this is probably a social and political question, so apologies in advance, but I was wondering what you thought about how the status quo can be changed. What kind of solutions can we have to such a desperate problem? Thank you.
Okay. Well, there's lots of ways it can be changed. I mean, as I pointed out, there's already 2,700 calories produced today per person in the world. So there's already plenty of food produced to feed the present population with the present rates, with the present development. The problem is, in my mind, so someone in economics is going to cream me for this, but in my mind, the problem is that food isn't a right. food is a commodity, right? We talk about commodities markets and everything else. As long as food is not a human right, you know, we don't have governance structures in institutions around to make sure that all people have access to safe food and drinking water. But drinking water is another really big one, right? So it's interesting, and I think this is, I think people understand this. Everyone is in their own silo. So, you know, USAID, for example, is you know, could do a lot, but in fact, what they rarely do is they protect U.S. farmers by dumping grain when there's excess grain, which really, you know, disrupts markets. You know, if you're dumping really cheap grain, it means like the incentive to grow grain in Africa goes down, right? Because there's all this cheap grain around. So it just practices, I think, of people realizing that food is a right. You know, it's not a commodity. That's a really tough sell, right? I mean, I'm not an economist, but I do know that they call them commodities, and there's these future trades and everything else. But I think fundamentally, that's once everyone publicly acknowledges that, you say, okay, how do I create governance institutions and actual institutions to move food around and create policies that really do make sure that people have access to it. I mean, most of the access problem today is economics, right? Poor people don't have access to food. Like I said, most of the people in the subtropics, almost everyone is involved in agriculture, but very few of them actually are growing food for themselves. They're growing food for someone else, and they're getting an income from it, and then they're buying food, right? So it's a problem. It's poverty.
Hello, thank you very much for a very interesting presentation. I have a question that relates to one of your slides that was showing the implications for food production of the changes in precipitations. And I think, if I understood correctly, it was showing that it had two time periods over the year, the December, February, and then the summer one, if you know the slide I'm referring to.
Yep.
I think you said that there would be precipitation would fall massively, that's the one, across Europe and the stand countries in December, February, with livestock implications and yield. But I was wondering about the June-August. We didn't really have a look at that, and also the implications for Scotland in all of or the UK, I should say, really.
Whoa. So, you know, I should have had time to actually look at the details of how reliable the Scottish ones are. Scotland is kind of on the edge. If I showed you the world map of precipitation. Okay, let me first say something else. We actually understand. You have a piece of chalk here somewhere? We understand. It's okay, I can do this. Oh, good. Okay, here's the equator. Let's say this is 30 degrees north and 30 degrees south. This is idea. You get the idea here. So pole would be this way, and this is my ground. And then I'm going up into the atmosphere. So I'm kind of looking at a cross section of the world. It should be like, I guess, this, right? Like this. Air basically is heated and goes up here in the tropics and comes down here in these subtropical regions. So air wants to come down these regions. And actually, this has been known since the mid-1800s. And this is very difficult to break. So most of the deserts of the world are at these latitudes. They're drier anyway, right? So what happens with global warming is basically the rich get richer and the poor gets poorer. So where it rains a lot, it rains more. And where it's dry, it gets even drier. And that's really basic stuff. It doesn't depend on how we treat clouds in the model. And so this region here is a region where it dries. And it dries in both seasons. The rainy season is winter, right, where most of the rainfall comes in southern Europe and in the stands, right? But it's quite a bit drier, and it's a very reliable thing. All climate models will give you that answer, whether you increase CO2 utopia or with business as usual, they'll tell you it dries there.
What about Scotland?
So Scotland, yeah. Well, Scotland will be warmer. It's, you know, the oceans heat more or less than the land. Less, right? Well, Scotland is kind of in the ocean, right? So, you know, so the temperature rise here is muted compared to the temperature rise in, say, Central Europe, right, or Central U.S. So let me go back to this picture here. Right, so let me just show you. Yeah, I can show you this one. So basically, you can see it's actually doesn't change at all in the central North Atlantic, right? But as you go across England, you're getting like maybe a 1 degree C annual average temperature. It'll be a little bit more in summer, right, than winter. But then as you go inland and you lose the kind of marine environment, the marine break, basically it just takes the ocean longer to warm up for the same amount of energy because the heat capacity of the ocean is so large that it just warms slower here. Now what happens to precipitation? If the storm track changes a little bit, it could be drier here, right? But if it doesn't change, the most likely thing is it just gets wetter. Yep. And unfortunately, it gets wetter in the summer. Actually, it's way drier here than it is where I live.
So,
in the wintertime, yeah.
yes, next question, please.
Hi there. I was wondering, do you think there's going to be much change in the geography of where the major sources of food production are? For example, moving away from the breadbasket towards Scandinavia, Northern Europe, Russia, and are those countries making provisions?
There's only so far north you can go, right? And certainly in the southern hemisphere, if you go farther toward the pole, you're in water, right? But if you go, the problem here is if you go north, it turns out like over a lot of northern Canada, there is no topsoil, really, because there was a big ice sheet over there that scrubbed it all off, right? So it's not good soil for growing stuff. Also, what's called the photoperiod, the timing when the sun comes up relative to the temperature cycles is different. So you have to adjust the crop stat. That's a hard thing to do, it turns out. So, and if you go up into northern Russia, like Siberia, it gets kind of peaty and wet and really extreme temperatures. Like, people have looked at this, you can't go too far north. And of course, that's hugely disruptive because you're moving people across boundaries, farmers across boundaries, and food across boundaries. For sure, you can't do much in the tropics. I mean, the stress in the tropics is going to be massive. No, it's just the only real good option here is to improve the crops so you stay on the optimal, and then you can still produce food at the kind of same rate in the mid-latitudes, and it won't be as volatile as it's going to be. And if you don't do that, like I said, though, that genetically people have been working on it, and it's a very, very difficult thing to do. There's been no progress so far.
Hi, you're right. You showed a slide which was showing the temperature from the year 1000 to 2100.
Yep.
There was a significant drop in the 19th century, the 20th century, sorry. Could that be replicated? And what was the cause of that?
Let's see, 20th, drop in the 20th.
So where it's like 1960?
Oh, yeah, here?
Yeah.
There's natural variability in here. There's also aerosols, which cool, right? So if you put aerosols in they're not a greenhouse effect. They actually most of the aerosols just block sun. Some absorb, but most of them block sun. So you can cool. So there's a couple of different explanations for this. Should I say aerosols is the answer?
Well,
it's
dodging the pumps probably, dodging the
yeah, there's that too. I guess, it's interesting because in 1995, the IPCC 3, so now we're at 5, came out and it said the balance of evidence suggests that humans have had a discernible, I'm not trying to avoid your question, had a discernible influence on climate. And a lot of us got, in the US for sure, that got most people involved in it because no one believed it. Right? People thought the data are not good enough, the models are not good enough. The forcing so far, the increase in CO2 is kind of small compared to all the other things going on. So my first reaction is, I think there's several possible explanations for that little dip there. One is that you had a lot of aerosols that were being burned at the time. It was before the Clean Air Act came in the US. There was an equivalent thing in Europe that started cleaning up aerosols, and so the air got cleaner, right? And so you had this cooling here, maybe due to increase in aerosols. Some people say there's just natural variability on multi-decadal timescales. I think you can't rule that out. There's changes in war, right? World War II had a really big change on air quality, on emissions and everything. So there's lots of possibilities, but the changes here are really pretty small compared to this 0.85 over the whole course of the century. If you take a climate model and you say, I'm not going to allow CO2 to change, I'm just going to let it freely go, and so it can wobble around just by weather and stuff like that, you see 0.2 degrees C changes in 20 years, plus or minus, but you never see 0.8. That's way out of bounds. So this change here can really only be explained by CO2 increases, and if you put those CO2 increases in the model, you get that answer. So it's a consistent answer. Right? Is that okay?
Great. Thank you. I think there was one up the top. Yeah, thank you.
Okay, so my question is, do you see any future in changing what kind of foods we eat from grains to, like people have been talking about eating bugs, and what are your like opinions on feeding kind of like cattle with grain?
Yeah, so if food supplies get tight, people will do what they have to do. I mean, most people are growing food or growing it because it's economical for a farmer. A lot of farmers would rather do business differently because it's more sustainable, but economically what they're doing is the right thing to do under the rules. The rules usually don't have sustainability as the governing principle. Certainly there are grains that do really well in heat. Millet, fantastic. Sorghum, really good, right? Apparently, even in Africa, where this stuff grows really nicely under really high temperatures, 30 degrees C, growing temperatures, people are moving away from that and growing corn. Now, I don't know if that's because of a cultural thing or just apparently it's really a pain in the neck to mill sorghum in millet, right? And so it's just a lot more work, and so people are not going to that, even though you could produce a lot more of those grains. Certainly, if you want to make the food supply efficient, basically you stop doing meat. Then you have a lot more grain to go around.
David, I'm Maggie Cusack from the University of Glasgow, and I just wondered if you could say a few words about the amount of CO2 going into the oceans and the acidification in terms of food security.
Okay. Yes. So one of the things that is really straightforward is that when you put CO2 in the atmosphere, it's in contact with the water and it dissolves in the water. And oh dear, what do you guys call soda here? It's something different. I saw it in the story the other day. It's the name for soda here. Huh? What? No, it's in the store and it's like some weird name. It's like well, it's like Iron Brew, But so it's you open it up and like it's carbonated, right? It's carbonic acid, right? It's got carbon dioxide in it, and so basically, if you put carbon dioxide in contact with water, some of it's going to dissolve and it's going to come up with equilibrium. If I just increase carbon dioxide in the atmosphere, more is going to dissolve in the ocean, and you can measure it, and the ocean's already gotten about 30% more acidic since pre-industrial times, the upper ocean in contact with it. And the outlook for the future, I mean, is really incredible. I think it's like a factor of 2 or 3 increase in the acidity of the upper ocean by the end of the century under the kind of split the difference emission scenario. And that's really basic chemistry. It's you can't avoid that other than paving over the oceans, right? So that's going to happen. Now, my impression is the impact on ecology is not well known. That there are some organisms that are really tremendously damaged by increasing CO2, and there's others that do okay, or don't seem to be affected. I guess this is not my expertise. Sandy's better answer this question, but my impression is basically you mess around with the very base of the food chain, the marine chain, and things are going to go up, right? And my impression is, with maybe very few exceptions, you actually don't know what's going to happen at the end of the day, but it's going to be different. And I guess the way I would look at this is like, I don't know, would you say that's? Yep. Okay. Okay. I did say it wasn't my expertise. But actually, so we have this massive beetle outbreak in Washington State and all the West now, in British Columbia. This is something that should have been easy to see, right? All it is you have mild winters, and you don't kill the beetles off, and they come back in force, right? This is really easy. Nobody saw this coming, right? That's a very simple relationship, and yet no one saw it coming. But after the fact, it's like, oh yeah, duh. You know, it's like, we know that. So my impression is that in the future, we're going to see changes. Because we don't understand the wiring diagram of ecology, and especially in the marine environment, we're not going to actually really know why those changes happen. There will be changes. And in some cases, we'll be able to trace them, like the bugs in Canada. In some places, we won't.
Do you envisage a major shift in the rice growing areas over the next 100 years? If so, would Scotland potentially become one?
Got a lot of water. A little bit higher temperatures would help a lot. It'll be interesting to see, for example, if California, which produces a lot of rice, gets out of rice. I mean, they should get out of rice, but the thing is that the dice is loaded in their favor, and if they can just get the Japanese market to open up to them, it'll be a killing. You know, it'll be like the gold rush. So I don't know. Certainly, you won't see big changes out of Southeast Asia. And that'll still be rice, big time. Scotland seems like it'd have to be a lot warmer here to grow rice. Maybe in greenhouses or something. Yeah.
Well, thanks very much, David, and thank you to the audience for coming here, then participating in the question and answer. So it's just my pleasure to ask us all to offer David a vote of thanks, not only for a very illuminating talk, but one delivered with a lot of passion and enthusiasm and a lot of creativity. And I think it's a better world when you've got creative people like David addressing some of the problems.
Yeah. Thank you all for coming, and really, I am so grateful to the Trust and to the university for allowing this to happen. And my wife and I are here, and we've been in and out of Scotland for years, and it's a real treat to be able to be back and to be part of the academic community this time. So thank you.